Okay, welcome to the Ashley Johnson Unit 5 Study Guide. All right, let's get started. We are first to complete and balance the following reactions. And we need to include the physical state of each of these products because the reactants already have their physical state. They're aqueous. So what do you need for this assignment? You need a periodic table and you need a solubility chart. Before we get started, let's go ahead and learn how to read this solubility chart because it's very important in helping us determine the physical state of each of the products in which we're going to have to do in this first problem. So if you notice, and there are millions of charts like this, but they all say the same thing, that we have the top of this in green. It says compounds containing the following ions are generally soluble. These substances are generally soluble, but there are some exceptions. For here we have lithium, sodium, potassium, and ammonium, but there are no exceptions. Mr. Schmidt is generally cool. What are the exceptions? None. There are no exceptions, so Mr. Schmidt is actually always cool. So these are always soluble. Same thing here. Nitrate, and then you have your acetate. No exceptions. They are always soluble in water. Then you have your chloride, bromide, and iodide ions. These are soluble, but they are not soluble when they're with silver, mercury, or lead. And then you have sulfate, which is generally soluble, but not soluble with strontium, barium, lead, silver, or calcium. If we go down this chart, we see that we have some that are generally insoluble. So these are generally insoluble. They will not dissolve in water except when paired with these things. Why is sodium on here? Why is potassium, lithium, and ammonium? Because they're always soluble. They're every one of them. So there's an exception because these are always. When paired with the S2, calcium, strontium, barium, the resulting compounds are soluble. And does this say the same thing? Okay, OH, same thing. Okay, so then you have your carbonate and lithium, sodium, potassium, ammonium. Notice it's the same thing here where they're always soluble. So these are generally insoluble except for with those cations that when paired with anything are soluble in water, meaning the water breaks them apart. So that's very, very important to what we're doing. I know I took a 2-minute spiel on that, but very, very important to the concept. So the first part of this is complete and balanced. We have to recognize that we have a double replacement reaction. And in a double replacement reaction, what you do is you're switching cations. Cations being the substance with the positive charge. How do we remember a cation has a positive charge? Well, what do cats have? That's right, cats have paws. So they're positive, right? So what is the charge of this lead? What is the charge of? We know it's positive charge, but what is the charge? It's one of those that, is it lead 2? Is it lead 4? I don't know. So in order to look at this, in order to know this, we have to look at the anion. And the anion tells us is nitrate. If we look at our polyatomic ion chart, we could see that nitrate always has a -1 charge. But we have 2 nitrates, so a total charge of -2. If the sum of the charges were going to be 0 for lead and the 2 nitrate, that means this lead must have a +2 charge. So we know it's lead 2. And then we know that potassium here has a +1 charge, and we know that sulfate has a -2 charge. All right. And so there's 2 positive ones for a total charge of +2, and then there's 1 sulfate for a total charge of -2. So just to show you that the sum of the charges do equal 0, even though I'm putting a 1 and a -2 here. But there's a reason why I'm doing that. Because we are going to switch cations. Lead and potassium are going to switch. Lead is going to switch to pair with sulfate. Potassium is going to switch to pair with nitrate. But we still have to make sure the sum of our charges equals 0 when we make these new compounds. For instance, we know that lead, we know it's lead 2 because we discovered that now, we looked at the math, is now going to pair with sulfate, and SO4 is 2-. So the sum of the charges here equals 0. We don't have to make any changes. We can write it very easily that way. Now, the next part, we have potassium. It's a 1+ charge. Pairing with a nitrate, which is a 1- charge. Once again, sum of the charges equals 0. KNO3. All right, now we need to balance. I'm going to erase some of this stuff at the top of the page so that we have a clear path to write. And we see that we have 1 lead, 2 nitrates, 1 nitrate, 2 potassium, 1 potassium, 1 sulfate, 1 sulfate. So we need 2 potassium and nitrate on this side in order for that to be balanced. It is now balanced. Check on your own time, but unless you want this video to be 45 minutes long, I'm going to have to just put that in there. So now, we have to go to the next part of our task. Include the physical state of each of the products. So, if we look at our solubility chart, and we find sulfates on here, we see that sulfates are generally soluble, meaning they dissolve in water. But there are some exceptions, and those exceptions are strontium, barium, lead 2. Well, what is our sulfate paired with? Lead 2. So what does that tell you? It tells you that it will not dissolve in water. So what it forms is a solid, and we're just going to put an S right there. Now we know that we have potassium and nitrate. Interesting thing about potassium and nitrate, potassium is always soluble, and so is nitrate. So that makes that a real easy one to understand, is aqueous. It will dissolve in water. And that is the end of that game. Way too easy on that one, unless I made a mistake. And then you'll text me and let me know about it. All right, so we now have aluminum chloride and silver nitrate. So, once again, look at your charges. Aluminum, 3+, chlorine, 1-, silver, 1+, nitrate, 1-. We're going to switch the cations. Now, aluminum is going to pair with nitrate, NO3, 1-. Do the sum of the charges equal 0? That's right, they don't. So let's put a parenthesis around this. I'm going to take this. We need 3 of these, and we need 1 of these. So now we're writing the correct formula. If you don't write the correct formula, this is going to be a really bad answer. So it's very important that this is aluminum, NO3, 3. All right, you have to put it with that ratio, a 1-to-3 ratio on that. And that's just so you're showing that the sum of the charges equals 0. Now you're doing the same thing with the silver. Silver has a 1+ charge, and then chloride has a 1- charge. So that's a very easy one, AlCl, right? And that's super easy. Now it's a matter of balancing the equation. If we want to balance the equation, we simply make sure we have the same number of each type of element on both sides of the equation, and therefore we'd have the same mass of the reactant, and the products would have the same mass, is what I meant to say there. So, and it follows the law of conservation of mass. So, what we have here is 1 aluminum, 1 aluminum. We have 3 nitrates, 1 nitrate. Uh-oh. We have 1, oh, I'm sorry, I put the wrong element there. Better correct that before I get a AgCl. Thought that looked weird when I wrote it. All right, sorry about that. So we have 1 aluminum, 1 silver, 1 silver, but we have 3 nitrates and 3 chlorine. So we need to fix that by placing a 3 right there, and I believe we have solved our issue. We have 3 chloride, and no, we have not solved our issue yet. So we need 3 nitrates here, and that should solve us. So now we have 3 silver, 3 nitrate, and 3 silver, 3 nitrate, and 3 chloride. So we're on both sides of the equation, and 1 aluminum on both sides of the equation. All right, so there we are. That's done. But now we have to make sure we know the physical states. we see that we have a nitrate, no exceptions. So that is going to be aqueous. And then we need to look up for this chloride. And the chloride falls under this category, chlorine, bromide, iodide. And when paired with silver, mercury, or lead, we have it paired with silver. So we know that it is a solid because silver is one of the exceptions. And that is all there is to that. Now these next problems, they're not super difficult. Notice you already have your states of matter, so that's very nice. What we have to do is we are charged with writing the total equation. Sometimes I call these the complete equation, but here he calls it a total, so we'll call it total. What you're doing there is when you see something is aqueous, you're going to break that up into its ions. And so you have Fe, and we need to know the charge of this iron. So because iron has multiple oxidation states. So we have -1. There's 3 of those for a total charge of -3. So this must be a +3. So this is 3 plus. Plus, now notice this 3 here. There's 3 nitrates. When you're writing a complete or total ionic equation, you're going to make these subscripts not for not something within the polyatomic, but outside the polyatomic. You're going to make it a coefficient. So it's going to be 3 NO3 1 minus plus. Now we have a coefficient 3. You're going to keep that a coefficient 3 K 1 plus, now you're going to distribute this 3 to this hydroxide, 3 OH minus, arrow. Now this forms a solid, so it does not break up. So it is Fe, Fe. We already know that it is a 3 plus. Oh, why am I trying to break it up? I just told you it didn't break up. It does not break up, so we're going to keep that a solid, OH3, and put a little S here so that your instructor knows that you know that is a solid. It is not soluble, so it does not break up into ions when dissolved in water. And then lastly, the KNO3, see that coefficient 3, K, 1 plus, 3, NO3 1 minus. All right, and that's all there is. That's the total or complete. Now you need to do the net. The net ionic equation only involves those things that form your solid. So the other ions that do not make up the solid, we call those spectator ions. Or spectator ions are potassium and nitrate, and normally I scratch through those, and I guess I will. You can write it on your paper, rewind the video, but if you want to write the total without lines through it. So we scratch those out, and then we just write what's left. So we have Fe 3 plus 3 OH minus gives us FeOH3 solid. And this will be balanced because we wrote our coefficients from the balanced equation, so we don't have to look at that. And that is the total and net ionic equation for that problem there. All right, same thing here. We need to know the charge of iron. Nitrate has a -1 charge. There's 2 of those, so this must be iron 2. This is a -1. So we have 3 Fe 2 plus 3, I'm sorry, this is not correct, plus, now, and I did that from racking wrong, didn't I? No, everything is good over here. All right. Where am I? There we are. We have 3 Fe2 plus plus, now pay attention to this. There's a 2 here, and we took that 2 out previously, and we multiplied it by the 1 in the coefficient. But now our coefficient is 3. So we're going to take 3 times 2, and we're going to get 6 NO3, 1 minus. All right, so 3 times 2 is plus 6. 6 times negative 1 is negative 6, so the sum of the charges was 0. Now we have 2 times 3 sodium, so that's 6 Na1 plus. Now, we have this 4 here, but this is a phosphate. That there are not 4 phosphate, there are only 1 phosphate. So it's going to be 2 PO4 3 minus. All right, because phosphate has a negative 3 charge. So you have 6 plus, 6 minus. Sum of the charges equals 0. Now you see your solid. Fe3, PO4, 2 for the solid there. It does not ionize, so we're not going to show that it breaks up into its ions. Then next, sodium nitrate. You have Na, 6 Na1 plus 6 NO3 1 minus. And that is your total ionic equation. So now you're going to do your net. First, remember, we have to get rid of the spectator ions, those things that do not play a role in the formation of the solid. So the solid does not have sodium, it does not have nitrate. It does not have sodium, it does not have nitrate. Write down the rest. 3, Fe2 plus 2 PO4 3 minus gives you Fe3 PO4 2 solid. And that is the game. Okay, for this next one, we're going to see that we have iron 2 carbonate, which is in the solid form, react with hydrochloric acid. Now, when this iron carbonate is placed in water, it will not dissolve. However, when it is placed in hydrochloric acid, it will dissolve, and we can see that by the reaction, because otherwise it would not. We would still have iron 2 carbonate over here as product. So this does dissolve when placed in HCl, so we're going to treat that as though it is going to break up, even though it is insoluble. But also notice these other states of matter. We have aqueous, gas, and liquid. All right, so we have here iron, hopefully my pen still works, Fe2 plus CO3 2 minus. And the reason we're breaking this apart is because it's reacting with this HCl. It's going to be dissolved in the hydrochloric acid, not water. Then we have 2H plus 2Cl minus. And that is going to give us Fe2 plus 2Cl1 minus. We know that because it's aqueous. But this forms a gas. This gas does not break apart. It is CO2. It does not ionize. It stays together. So we're going to keep that a gas. And then also water. It produces water. And guess what? Water does not dissolve in water. Do not make water aqueous. Water is never aqueous, because water does not dissolve in water. Water is a liquid. All right, so keep that in mind. Now we're going to have to do. Now all we're going to have to do is. So this is our total. Now all we're going to have to do is our net, and we're going to only keep those things that form the gas and the water. So our spectator ions are iron and chloride. iron and chloride go away. By convention, I like to leave my cation first, so it does not matter, but I'm doing that. Plus CO3, 2 minus. It's going to give us CO2 gas plus H2O liquid, and this should be balanced. So, and you could put aqueous here, I guess, if your instructor is particular, but make sure you label those gas and liquid for sure. But someone could determine that these are aqueous just by the presence of an ion they broke apart. So what we should see is that this is balanced. So we have 2 hydrogen, we have 3 oxygen, 2 plus 1 oxygen, so that's good, and we have 1 carbon, so it's balanced. And that is the name of that game. This is the study guide. I believe it's questions 1 and 2. I'll try to get to some more here shortly. Thank you.